Yes, hello there, it's Ashraf here, and today I want us to look at development by triangulation. Now, just to give you a simple recap, we went through development, how we can develop a cylinder, if you remember correctly, how we can develop a cylinder by getting the ordinate distance and marking it off 12 times here. And by doing that, you develop a cylinder. Then we also learned how we can develop a cone. How we can develop a cone. And we said, simply get the true length, stand here, draw an arc, ordinate distance, mark it off 12 times here, and then you've developed a cone. We saw that. But then there are pieces that look like this, and we call these transitional pieces. Transitional pieces are pieces that have a different. Now, when you look at this, the top part here is a square. It's a square. And the square is tilted, and then the bottom part is also a square, but the normal square. So we cannot develop this using this formula for cylinders. We cannot develop this using this formula for cones. So we call this a transitional piece. Then we have this also. The base, as you can see, it's corresponding to the base down here. The base is a square, and then the top here, the top is a circle. So this is a transitional piece. The base differs from the top. So that makes it a transitional piece. We can't develop this using the cone method. We cannot develop this using the cylinder method. So that implies we have to use development by triangulation. Now, as you can see, development by triangulation comes from the word triangle. Triangulation comes from the word triangle. So that implies we are going to apply triangles here. So how do we do this? Perfect. So what you do, you first draw this accurately. So I'm going to fast forward this video and draw this accurately. Then we resume. Perfect. Okay, perfect. So I've drawn this accurately. As you can see, this is my plan and this is my elevation. Someone may be wondering how I drew this. What I did is simply drew the normal square. Remember, this was square 25. So I drew a normal square. I put the diagonals in. Then I simply measure this distance here. It's going to be the same for all corners. So I transferred it to the center of this, and I simply join. So that's how I got that. Perfect. So what you do, you're going to name. So this is A, B, C, and D. And then I'm going to name these corners as 1, 2, 3, and 4. Perfect. Now you can see that 1 and 4 will correspond to this point on the base. So this is 1, 4. Then this 2 and 3 is here. 2, 3, because this line is representing the base, and the base is that. Okay, then the top is this. So you can see that this point will be A, C, and then this point here will be D, and then this point here will be point B. So then I'm going to introduce a new concept. We call it a seam. And what we call a seam is the cutting edge. So my seam here is going to be this. I'm going to represent it with a dotted line. So my seam is going to be DX. I'm calling this X. And to demonstrate a seam, so I was saying, to demonstrate a seam, I've rolled a simple cylinder here. So this is my cylinder. A seam, I'm saying a seam is the cutting edge. If you want to develop this cylinder, this is a cylinder, we have to cut it somewhere. And that point where we cut it from, that is where we call, that's the point that we call a seam. So if I'm cutting from here, that would be the seam, and that cutting line is the seam. So, and it opens like this. So seam and seam. So I hope we get the concept of a seam. So the seam in this case is X and D. So that would mean that we are cutting this transitional piece from right here. And when we cut it, we can be able to open it and see its development. So that is basically development. Seeing, I don't know if you've made boxes, but if you open the box and try to flatten it, that shape that you get is the development of that box. So it's the same idea here. Development, you're trying to see what forms a material. So when we say we are developing this transitional piece, we are trying to see the nature of the material that was used to form the material. Hence, development. Perfect. So this is the cutting edge. And remember, we are doing development by triangulation. That means you are going to employ triangles. So this is what I mean. I create a pattern along the surface of this transitional piece. This is my plan, this is my elevation. So join D to 1. This is a thin and faint line. Now you realize that I've created my first triangle, and my first triangle is XD1. So that is a triangle. Then I can join A to 1. That would be my second triangle. 1DA1, second triangle. Then A2, triangle, 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 and triangle, and finally the last triangle right there. So as you can see, I've created a pattern of triangles around the surface of this figure. So we can start our development. Then, by the way, these lines that we've created, you can also trace them down here on the elevation. So line D1 is this line D1. Then line A1, so I can join A to 1 down here. So that would mean this line here in the plan is the same line here in the elevation. Then A2 here. Then we have B2, that one. Then B3 here. Then C3 here. I hope I make sense. Perfect. Now, this is what you do. You're going to come to the elevation and you're extending a vertical line at a small point, a small distance away from this line here, and do something like that. Then you're going to start from our seam. So what you do, I'm going to introduce the concept of true lengths here, and that will have us borrow some knowledge from a topic called lines in space. Perfect. So what we do is that we are going to determine the true lengths of all these lines and use those true lengths to develop the profile of this transitional piece. So this is what I'm talking about. I'm going to start at the seam, my cutting edge here. I come and I pick the plan length XD. So this plan length XD, I have to determine its true length. So what do? I come to my line that I drew here. I mark off that plan length down here. Then I join this point up here. And then I pick this distance. So this distance, ladies and gentlemen, is the true length of XD. This line XD, the true length of XD is this. So this is the length that you are going to use to produce a development. This is what I'm talking about. So you're going to draw a line at any angle that you want to start off your development. Then I'm going to pick this true length of XD, my cutting edge, come over here, mark it off. So mark off. So the point up is D, so D, and then the point down is X. So I've started like that. Then to complete my first triangle, remember our first triangle is XD1. We need to get point 1. So to do that, we get this plan length D1. So come and mark it off along this line like we discussed and said. Then once I join this point up here, this line that I get gives me the true length of D1. I hope I make sense. So the true length of D1 is this line here that I've put in this. So we are going to stand at point D. Why D? Because we are trying to locate 1. We already have X, we already have D, so I am standing at D. So D, and then I draw an arc. So that would mean that this point 1 lies along this arc. So how do we get point 1? That would mean we need distance X1. And since X1, we can all agree that X is here, 1 is here. So the plan length is X1, but in the elevation, X1 has no height. You can see that it's just a point. So that would mean that the true length of X1 remains this very one. So I'm simply going to pick X1, come and stand at X and mark off along this arc. And this, ladies and gentlemen, is my point 1. So I join this and then I join here like that. And as you can see, I've created this first triangle. Then I proceed to the next triangle, and we are going to use exactly the same procedure, ladies and gentlemen. So what do? Exactly the same thing. So we need to get point A to complete the second triangle. As you can see, this is a pattern. So I get the distance A1, this distance, come right here, mark it off. You're going to realize that it's the same as the last one. So this distance here is the true length of A1. So this is the true length of A1. So where do I stand? Remember, this is A1. I already have 1. So that means I stand at 1 and I draw an arc. See that? So that means point A lies along this arc. So to get A, I simply need to get the distance from D to A. So the distance from D to A is this one. And then if I can take you back to lines in space very little, this is what we are discussing. We discussed and said in lines in space, if you have a line, I'm going to call it AB, this is the elevation, and then the plan is purely horizontal, A prime, B prime. The plan is purely horizontal, these angles are 90. We said the true length of that line AB would be this slanted line. Not so. Let me give you a second scenario. We also discussed and said that if you have the elevation AB slanted and you also have the plan A prime, B prime also slanted, none of these is the true length of that line. So you would be required to find the true length of this line. Remember that. Perfect. That's why, if I can take you back slowly, that's why for line D1, you realize that in the plan it is slanted. Focus your attention on line D1. In the plan it is slanted, and also in the elevation D1 is slanted. That's why we are getting the true length of D1 besides here. Then if I can take you back to XD, as you can see, XD is purely horizontal. Focus on XD. And then XD in the elevation is slanted. So that would mean that the true length of XD is this slanted XD in the elevation. So if you can remember correctly, we got the true length of XD, and the true length of XD was this very one. Let me measure it from the development here. Was this one, the true length of XD. But if you measure it off here, it's going to be exactly the same as this. Why? Because the same concept applies. XD is purely horizontal in the plan and is slanted in the elevation. So what is slanted is the true length of that line. Now, we are going to apply the same concept on line DA. I don't know if I'm still with you. If you're lost, try to rewind back and rewatch and try to get this concept. So I'm on point DA. Remember, I have D and I'm trying to locate A along this curve. So as you can see, DA in the plan is slanted, and the same DA in the elevation is purely horizontal because point D is this and point A is this. So this is purely horizontal DA, and then DA in the plan is slanted. So that would mean that this DA that is slanted is the true length of DA, applying this concept. So that would mean I simply measure DA, come right here, mark off A, so join. So my second triangle is also ready. I don't know if I make sense. So we proceed to the third triangle, and in this we need to get point 2. So that would mean I need to get A2, the true length of A2. As you can see, A2 is slanted and A2 is also slanted. So we need to get the true length. So A2, same point. That means you're measuring this distance still. So A2, we already have point A. So that means I'm standing at A. Because I'm getting A2 and I already have A. Stand at A, draw an arc. Then we need to get the true length of 1, 2, because we're trying to get 2. So we need to get the true length of 1, 2. But as you can see, 1, 2 is horizontal, 1, 2 is horizontal. So any of these two lines is the true length of that line. You see that 1, 2 will be the same as 1, 2. So 1, 2. Yes, please, that lines in space concept, try to understand it. If you don't, rewind and rewind several times and understand it. Then we are proceeding to the next triangle, which is A to B. So that means I need to get the true length of B2. So B2, get that, stand right here. It's going to be the same as this. Stand right here, measure this off. Remember, you're getting B2. I already have 2, so I stand at 2, draw an arc like that. Then along this arc, that's where I have B. And as you can see, I need to get the distance AB. So AB is slanted in the plan, but AB is purely horizontal in the elevation. So that would mean this slanted one is the true length. So I measure this. that, come to this point, mark off. So this is A. So that triangle is also ready. So let's proceed. The next triangle will be, this is supposed to be B. The next triangle will be B2, 3. So what do? You need to get the true length of B3. So pick B3 and realize it's going to be the same as this. So I'm going to pick this. I'm sure you're getting now the pattern. So I'm going to be a little fast. So I'll stand at B. Why B? Because I'm getting B3. I already have point B. So stand at B, mark off. Then I need to get the distance from 2 to 3. And like we said this time, this side, 2 to 3 has that distance in the plan, but 2 to 3 in the elevation is simply a point. As you can see, 2 and 3 are on the same point. So this would imply that this distance is the true length. So measure it, bring it right here. So this point here is 3. Join. I'm going to outline these right away because we know they are going to be outlined. So outline this, outline this, outline this. Let's proceed. So B3 we need to get now BC3. So to get that I need C3. So get the true length of C3, bring C3, it's going to be on the same point, pick this distance right here. Then we are standing at 3. Why? Because we are getting C3. You already have 3, so stand on 3, draw an arc. Then you need to get the true length of BC. BC is purely horizontal here, BC, and slanted up. So this slanted one is going to be the true length. So BC. Join. So this is C. Outline this line. And then now that we have C, we need to get C4. We need to proceed to the next triangle, which is C3, 4. So I need simply to get the true length of C4. Realize it's going to be the same as this. Pick this. And like we said, you're getting C4. You already have C, so stand at C. Draw an arc. Draw an arc. Then get the true length of 3, 4. 3, 4 is purely horizontal. 3, 4 is purely horizontal. So any of these is the true length. So 3, 4 there. So this point here is 4. Join. Then now that we have 4, we need to get 4. We need to get triangle C4D. So I'll get the true length of 4D. 4D. Stand at 4. Sorry, get the true length of 4D. Get the true length of 4D here. This. So stand at 4. Draw an arc. Then get the true length of CD. And CD is purely horizontal in the elevation and slanted in the plan. So this length here will be the true length. So stand at C, mark off. This point here is D. Join. And this is 4D. Then finally we need to get the last triangle, which is 4DX, such that we can come back to our scene. Perfect. So that would mean that I need to get the true length of DX. You already have 4 and D, so we need to get DX. And remember we said DX is purely horizontal but slanted in the elevation. So that would mean that the true length of DX, this guy, is actually this, because this is purely horizontal. So I'm simply going to measure this. If you're not sure of that, you can pick this plan length, come and mark it off here and get the true length. So I'll stand at point D because I'm getting DX. Then the true length of 4x is going to be 4x. I've already explained why. So this is point X and I close this off like that. Perfect. And what we've created, ladies and gentlemen, is a development. So name this as your plan, name this as your elevation, name this, you're going to name this, though my diagrams intersected each other, but that's not good practice. Make sure yours will not. You're going to name this diagram on the side as the true lengths. because we've been measuring all the true lengths from here. So put it down here somewhere, true lengths. Then name this as your development. Then another task that you can do is you can cut this development out. If you cut it out and try to join it, try to join x to x and d to d, you're going to form that transitional piece that forms the actual figure of this. So try it out for your own understanding. Thank you very much for watching. See you in the next video, and we shall be looking at the next transitional piece, which will have a circle in the center this time. See you then. Bye for now.